This is Module 16, Section 10.3. In this section, we're going to look at rules that will help us simplify radical expressions. So the first rule we're going to look at is called the product rule for radicals, which simply says this: if you are multiplying two radicals together, and each of those radicals has the same root, for example, they're both square root terms or both cube root terms, when you are multiplying each of those together, you can combine that into a single radical expression by writing one root sign and then simply doing the multiplication underneath the sign in the radicand. For example, the general rule there is stated as the nth root of a times the nth root of b is the same as the nth root of a times b, all under one radical sign. Now often this will allow us to simplify radicals in an easier fashion, or sometimes if we do the product rule in reverse and actually split out a fairly complicated radicand by splitting it out into two or more radical terms, that often makes our life easier as well. So for example, let's look at this particular problem. Let's say that you are asked to simplify the square root of 3 times the square root of 7. Now, square root of 3 cannot be simplified any further. 3 is not a square root, and there aren't any square roots in that. Square root of 7, same thing. 7 is not a perfect square. Since we're multiplying those two, though, we can write that underneath one square root symbol and do the multiplication underneath the sign. So now we have the square root of 3 times 7, and that gives us a single simplified expression of the square root of 21. 21 cannot be simplified any further. 21 is not a perfect square, nor are there any perfect squares in it. Okay, now let's say that we were asked to find the fourth root of 8 times the fourth root of 2. Again, since that's a multiplication problem and both of those radicals have an index or a root of 4, we can do the multiplication step underneath a single radical sign. So we've got the fourth root of 8 times 2, which is the same as the fourth root of 16. And 16 is a perfect fourth root. Turns out that positive 2 is the fourth root of 16 because 2 to the fourth, or 2 times 2 times 2 times 2, is 16. All right, let's look at this problem then. We're taking the cubed root of 3 over m, and we're going to multiply that to the cubed root of n over 5. Okay, those are identical roots. They're both cubed roots, so we can combine that into one big cubed root expression. And we've got 3 over m times n over 5 is the same as the cubed root of, multiply straight across, 3 times n is 3n, and m times 5 is 5m. And finally, let's say that we were looking at the fourth root of ab squared times the fourth root of 27ab. Combine that using the product rule for radicals under one radical sign. That would be ab squared times 27ab and now use rules of exponents to combine all that. That gives us the fourth root of 27a squared b cubed. All right, now let's look at one more example up here in the upper right-hand corner. Let's say that you were trying to simplify this problem. The cubed root of 8x cubed y to the 6th. For this particular example, using this product rule of radicals in reverse is actually going to help us simplify it. Notice that there is multiplication steps underneath that radical sign. And what product rule for radicals says is if you have multiplication under the radical sign, you can split that term out into its individual factors with a sign for each factor if it allows you to help simplify the problem. And in this case, it will. So what we're going to do is we're going to split that cube root out to the 8, and then multiply that to the cube root of x cubed, and then multiply that to the cube root of y to the 6th. Okay, that's the product rule in reverse. And the reason that helps us is the cube root of 8 is a perfect cube, is 2. 2 times 2 times 2 is 8. The cube root of x cubed is simply x, okay, because x times x times x is x cubed. And the cube root of y to the 6th, what value multiplied by itself 3 times gives us y to the 6th, is y squared, because y squared cubed is y to the 6th. So by splitting that particular radical term out, that allows us to simplify down to an answer without radicals. So for the product rule, sometimes it helps to combine radicals. Sometimes you can use it to split radicals out and simplify. There's also a quotient rule for radicals, which is very similar. The quotient rule says if you're taking the nth root, some root of a fraction, a divided by b, you can, if it helps you, split out that fraction into equivalent radicals that can then be simplified separately. Or, in some cases, you might need to do the reverse. You might need to take a numerator radical and a denominator radical, and as long as they're the same root, both square roots, both cube roots, both fourth roots, it might be helpful to combine it into a single term and then simplify the fraction that way. So let's look at some examples of that. Let's say that you were doing the square root of 6 over 49. Okay? Square root of 6 over 49, using the quotient rule of radicals, could also be written as the square root of 6 divided by the square root of 49. And although that didn't help us much in the numerator, 6 is not a perfect square, so we'll have to just leave that as the square root of 6. Square root of 49 is a perfect square, and it allows us to at least simplify our denominator into an integer number of 7. So the square root of 6/49 is equivalent to the square root of 6 divided by 7. Our next example has this. We've got the fourth root of a cubed divided by 81. A cubed divided by 81 cannot be simplified, so let's try splitting it out using the quotient rule. That's the same as the fourth root of a cubed divided by the fourth root of 81. Now again, with our numerator, there's not much we can do there. You can't take the fourth root of something cubed, and so that will just stay as the fourth root of a cubed. But 81 is a perfect fourth power. Okay? 3 times 3 times 3 times 3 is 81, and so the fourth root of 81 does simplify down to 3. Okay, another example. Let's look at using the reverse to help simplify. Let's say you had the square root of 45 divided by the square root of 9. Okay, now your initial instinct might be to simplify in the denominator. Square root of 9 is 3, and that's something that you could do, but notice that if we recognize that we've got a fraction and it's the same square root, if we take that and now put it under a single root symbol. So we rewrite it as the square root of 45 divided by 9. 45 divided by 9 is even division. That gives us the square root of 5, which is simpler than the square root of 45 divided by 3 had we tried to simplify it in its original form. And in math, you always want the simplest answer possible. Okay, so this fourth example, let's look at this. And I'm going to bring it up here. We're going to look at the square root of a to the 7th, b to the 6th, divided by the square root of a cubed, b squared. Okay, right now there's separate square root symbols in both the numerator and the denominator. What we're going to do is we're going to write that entire fraction under one radical sign, at least initially, to see if that helps us simplify some of those individual factors. Now, looking underneath the radical sign, notice that there is some simplification we can do. Okay? Ignoring the radical sign, just looking at the fraction, we've got 7 a's up top and 3 a's down in the denominator. So we can cancel out 3 a's, both top and bottom, or you can use the subtraction rule for exponents if you want. If you take 3 a's out of the denominator, they're all gone. If you take 3 a's out of the 7 a's up top, 7 minus 3 is 4. So you're left with a to the 4th. 7 minus 3 is 4. And ditto with the b's, you've got 6 b's up top and 2 b's in the denominator. So if you take 2 b's out of both top and bottom, 6 minus 2 leaves you with 4 b's up in the numerator. So now we've got, if we bring this over here, the square root of a to the 4th, b to the 4th, divided by 1, or the square root of a to the 4th, b to the 4th. Now we could split it back out into individual fractions, or terms, I'm sorry. Square root of a to the 4th times square root of b to the 4th. Is a to the 4th a perfect square? Is there some number when you multiply it by itself or when you square it gives you a to the 4th? And the answer is yes, a squared. A squared times a squared is a to the 4th. And the same thing is true with the square root of b to the 4th. Is there a number when you multiply it by itself that gives you b to the 4th? And the answer is yes, b squared. And so what started off as what looked like a pretty difficult problem fell out nicely by using the quotient rule in both directions. Another rule that's very helpful when trying to simplify radical expressions is writing a radical term so that the index or the root matches the power that goes with the base underneath the radical sign. And remember that power can also be written outside of the radical sign. Okay? In other words, remember from earlier, the nth root of a to the n is equivalent to the nth root of a to the n. Either way, the exponent can be written underneath the sign or it can be written outside of the radical sign. It's equivalent. If you can get your power to match your index, that power and index cancel each other out. They're opposite operations. Okay? And if they cancel each other out, then you also no longer need the sign because you're no longer taking any root. The root canceled out. To prove that to you, remember that you can always take a radical expression and rewrite it using fractional exponents if you want to. So this is the same as a to the power is the numerator and the index is the denominator, a to the n divided by n power, which is the same as n to the first, because anything divided by itself is 1, and anything to the first power is itself, which ends up just being the base. And that's what this says. If you're taking the nth root of a to the n, the answer is simply whatever the base is in the original problem in either case. Okay, but you have to be careful. If n is even, if you're taking square root, or fourth root, or sixth root, or eighth root, the value of a will always be the positive value. It will always be the absolute value of a. Unlike if n is odd, if you're taking cube root, or fifth root, or seventh root, or ninth root, the value that you get out is always just the value that a is originally, not the absolute value. Which I know is pretty confusing until we do some examples. So let me show you some examples. Let's say that you were asked to take the cubed root of -2 cubed. Now in this example, notice that the power and the index match. And so using the rule up top, because 3 is an odd number, this rule says that the nth root of a to the n should just be whatever the a is in the original problem. Remember that if the power and the index match, they're going to cancel because of this. Anything divided by itself is 1. And if you're getting rid of your index here, this radical sign has no meaning, so it's also gone. And so this says our answer is whatever our a value originally was, which is -2. Now let's do that longhand and make sure that that actually works. If we're taking the cubed root of -2 cubed, let's do the math under the sign first. -2 cubed is -2 times -2 times -2, which is -8. So now we're taking the cube root of -8, and hopefully you'll agree with me that the cubed root of -8 is indeed -2. As opposed to this example, let's say you were taking the fourth root of -2 to the fourth. Now the basic approach to the problem is the same. If the power matches the index, they cancel each other out. And if you don't have an index anymore, you also don't need the sign. And so initially you might think, well, then the answer is -2. But notice that this up here says that if your root is even, and it is, we're taking the fourth root. If your root is even, the answer is actually the absolute value of whatever a is. In other words, the rule says you're going to take the absolute value of -2, which ends up being a +2. Now let's look and see why that is. Let's do it longhand. If we're taking the fourth root of -2 to the fourth, and we do the work underneath the sign first, we would have the fourth root of -2 times -2 times -2 times -2, which is now the fourth root of 4 negatives being multiplied, is an even number of negatives. That makes it a positive value under the radical sign. 2 times 2 times 2 times 2. 2 times 2 is 4, times another 2 is 8, times another 2 is 16. But it's a positive 16 because negative times negative times negative times negative is a positive. And the fourth root of positive 16 is a +2, not a -2. So that's one subtlety you have to watch out for when you're using this rule. If you have an even root and your base is negative here, it does end up turning positive for your final answer. So let's look at this. Simplify the fifth root of x to the fifth. This is a very straightforward problem. You don't have to worry about the absolute value because it is an odd root. If your power matches your index, they cancel each other out and the sign is gone, and the base that is left is your answer. The fifth root of x to the fifth is x. Here, if you're taking the square root of negative x quantity squared. Again, your power and your index match, and so they cancel themselves out. If your root completely cancels out, the sign goes as well. But because this is an even root, the answer is not negative x, but rather it's the absolute value of negative x, which becomes a positive x. Okay, so just a little bit of subtlety there. All right, here's another rule that can simplify some of the work when you're doing radical expressions. And it says, if you're taking the npth root of a to the mp, that's equivalent to the nth root of m. In other words, if you have a common factor in your power and your index, you can cancel those out and simplify it down to a simpler form. And if we look at that in terms of rational exponents, the npth root of a to the mpth power could be rewritten as a to the mp divided by np fractional power. If you have a common factor in a fraction, you know that they will cancel out because anything divided by itself is 1. And that does simplify to a to the m over n, which will then convert back to the nth root of a to the m. Okay, so let's look at some examples of that. Let's say that you were asked to find the 14th root of x to the 6th. Okay, if you look at the 6 and the 14, if that was a fraction and you were asked to reduce that fraction, there is a common factor that you could factor out, because 14 can be rewritten as 2 times 7, and 6 can be rewritten as 2 times 3. So common factor of 2 will cancel out, and this simplifies down to the 7th root of x cubed. Now there's really nothing further you can do with that particular problem, but a smaller root is considered better in most cases. All right, now let's look at the 6th root of 2 to the 4th. Again, you could multiply 2 to the 4th out since we have a constant instead of a variable there, but rather than do that to work with smaller numbers, you can also take that same problem and look for a common factor. There is a common factor of 2 here, so 4 divided by 2 is 2. 6 divided by 2 leaves us with 3, and that comes down to the cubed root of 2 squared, which of course is the same as the cubed root of 4. Not much else you can do with that. 4 is not a perfect cube, and there's not any cubes inside of it. Let's look at the square root of x to the 8th. Remember that if there's nothing written out on the leg of your radical sign, it is an understood square root, which is a root of 2. So let's put that in, since we're going to look for common factors. There is a common factor between 2 and 8, and it's 2. So if we take 8 and divide it by 2, we're left with 4. 2 divided by 2 leaves us with 1. And there's no such thing as a first root. So in essence, what you've done is you've canceled out everything on the leg of the radical sign. And as with the previous slide, we said if everything is canceled out on the leg of the radical sign is no longer needed, so it is also gone. Okay? And what we're left with then is whatever we're left with underneath our radical sign, and our answer is x to the 4th. In other words, x to the 4th squared gives us x to the 8th. Okay? Let's look at one more example up here. If we're looking at the 4th root of a squared b to the 12th. Now here, you want to be careful about canceling out too early. Because if you decided, for example, that there is a common factor of 4 between that 4 and that 12 and you canceled out there, you would get the incorrect answer because this fourth root not only has to go to this factor, but also to this one. So the best way to handle a problem like this, where you have more than one factor under the sign, is use the product rule, which we talked about earlier first, and split that out. So the fourth root of a squared times b to the 12th is the same as the fourth root of a squared times the fourth root of b to the 12th. You've now split that radical sign out to each factor individually. And now you can reduce, okay, because the index is now going to each factor separately. Here there's a common factor of 2. 2 divided by 2 is 1. 4 divided by 2 is 2. And here you have a common factor of 4. So 4 divided by 4 is 1. And if everything cancels out there except for a 1, your sign is also gone. And 12 divided by 4 is 3. So what you're left with here then is the square root of a to the first, or the square root of a, times b cubed, no radical sign because we completely canceled out the root. And normally you write values or factors that do not have radical signs first. So we're going to write the b cubed first, followed by the square root of a. And remember that square root is understood, so if you'd like to drop the index of 2, you can, and get a final answer of b cubed square root of a. Okay, so now we are going to use these properties of radicals to simplify radicals into simplified form, or what's often called simplest radical form. So we have to know what the rules are. What is considered simplest radical form, which from here on out I'm just going to abbreviate as SRF, simplest radical form. Okay, here are the 4 basic rules for simplest radical form. Rule number 1. All factors in the radicand have exponents less than the index. Remember, radicand is what is underneath the radical sign. So for example, let's say you're working a problem and you get it down to this point right here, the cubed root of y to the 5th. You know that you're not done yet because the exponent of 5 is a larger number than the index of 3. So there is something more that you can do with this, and in the next few examples I'm going to show you what. For right now though, I just want you to know that this is not simplest radical form because 5 is a bigger number than 3. There's something more you can do. Rule number 2. No fractions are allowed under the radical sign for your final answer. So again, let's say you're working with a problem and you get it down to this. You get it down to the square root of 3/5. Okay, you know there's something more you can do because you have a fraction underneath the radical sign, and that is not allowed. Okay, so I'm going to show you again how to deal with that a little farther down the road. Right now, just know that this is not simplest radical form. You are not done yet. Rule number 3. No radicals are allowed in the denominator of a fraction. So let's say you're working and you end up getting it to this point. 4 divided by maybe the cube root of x. Okay, just like rule number 2, okay, you are not allowed to have a radical sign in the denominator. Notice there's not one in the numerator here, but because there's one in the denominator, this is not done. You are not in simplest radical form. And finally, the greatest common factor of the index and the exponents of all the radicand factors is 1, which is a fancy way of saying if you can reduce, you should reduce. So if you had, say, this problem, the 8th root of x to the 4th, because there's a common factor of 4 between that 4 and that 8, you can't stop there. Okay? If there's more reduction to be done, you must do so. This, again, is not simplest radical form. And I'd like to back up just for a minute to rules 2 and 3 here. It should occur to you that there's one type of fraction radical example that we didn't cover here, and that's what if you're working a problem and there is a radical in the numerator, but in the denominator you don't have a radical. Okay? We dealt with fractions under a radical. We dealt with a radical in the denominator. What about if you have an answer that has a radical in the numerator only? Is that okay? And the answer is yes, it is. This is simplest radical form for this example. There's nothing more you can do or should do. So radicals in the numerator by itself is fine. You just can't have a radical over an entire fraction or a radical in your denominator for a final answer. Okay, so for the remainder of this section, I'd just like to do a bunch of examples using the rules that we just reviewed and the simplest radical form rules that we need to follow for final answers, and see if we can simplify all these radicals down to simplest radical form. All right, so let's look at this example here. Let's say you're asked to simplify the square root of 56. Now, 56 is not a perfect square, but you could break 56 down. Notice that 56 is the same as 4 times 14. Okay? 4 is the same as 2 times 2, and 14 is the same as 2 times 7. Now your goal is to find perfect squares because this is an understood square root. So if you use that rule that we talked about where you can get your power to match your exponent, what we're interested in is trying to break down 56 using factors that appear twice. And notice that what we have here is 2 does appear twice, so we could rewrite 56 as 2 squared times, now do any other factors that are remaining appear twice? And the answer is no. We have a 2 and a 7 left, but since neither of those appear twice, there is no perfect square there. So you can recombine that as 14 if you want to. So the square root of 56 is equivalent to the square root of 2 squared times 14. Or you could just recognize that 4 up in this step is a perfect square and leave it as 4 if you want. Okay? So 56 is 2 squared times 14 or 4 times 14, which is the same as the square root of 2 squared times the square root of 14. We use the product rule of radicals there. And remember that if your power and your index match, they cancel themselves out and your sign goes. Or another way to think about that is the square root of 4 is 2. Okay? And that's an even root, so it would be the absolute value of 2, which is still just a positive 2. So we've got 2 simplified from that first term, first factor. And then square root of 14, there's really nothing you can do with the square root of 14. There aren't any perfect squares in 14. We know that right here when we did our factoring tree. So we're just going to leave that as the square root of 14. And this is our simplified answer, 2 square roots of 14. Recognize that this is multiplication. There's multiplication between the 2 and the 14. You know that because this was multiplication here. Okay? So simplest radical form of the square root of 56 is 2 times the square root of 14. All right, so let's look at then the fourth root of 81x to the 12th. Now your first instinct might be to notice that there is a common factor between the 4 and the 12. But you don't want to do that yet because it's not just x to the 12th that's underneath that radical sign. It's 81x to the 12th, which is multiplication. There's two factors there. So use the product rule of radicals to split that out to each factor individually. So we've got the fourth root of 81 times the fourth root of x to the 12th. And look at each of those individually. Let's start with the 81. 81, if you break it down, is the same as 9 times 9. And each of those 9s will break down to prime factors 3 times 3. And we're looking for our power to match our index. So we're looking for a fourth root. Are there any factors that appear 4 times? And the answer is yes. Turns out that all those factors combine to give us 3 to the 4th power. In other words, 81 is a perfect 4th power. And so to take the 4th root of it, you're taking the 4th root of 3 to the 4th. Your power matches your index and your sign goes. And this simplifies down to the absolute value of 3, which is 3. Or, if you just think about it in your head, the 4th root of 81, what number multiplied by itself 4 times gives you 81? The answer is 3. 3 to the 4th is 81. Okay. Now over here, we also have to simplify this. We've got a common factor. 4 divided by 4 is 1. 12 divided by 4 is 3. Because we canceled out everything on our radical sign, and we're left with a 1, our sign also goes. And so this comes down to a simplified form of x cubed. And so the 4th root of 81x to the 12th is equal to 3x cubed. All right, let's look at the square root of x to the 7th. Okay, now there's a trick to use here that makes simplifying these exponent radical problems fairly easy. First thing you want to remember is understood square root has a 2 out here on the index or the root, so I'm going to actually put that in. Okay. You know this isn't simplest radical form because your power of 7 is larger than your index of 2. If your power is larger than your index, there's always something more you can do. But unlike the problem above it, where we actually had a common factor of 4 we could factor out, there is not initially a common factor that you could take out of a 2 and a 7. Okay? In other words, if that was 2/7 as a fraction, you couldn't reduce that, or 7/2. So what we're going to do is we're going to try to take x to the 7th, and we're going to rewrite it so that we do have an exponent that can be reduced by that index. So here's what you want to do. Take the power that you're given in the original problem and ask yourself, will 2 go into 7 evenly? And the answer is no, it won't. So then start decreasing that power by 1 and ask yourself the same question. If 2 won't go into 7 evenly, will 2 go into 6 evenly? And the answer is yes, 2 will go into 6. So what we're going to do is we're going to take x to the 7th and we're going to rewrite it as x to the 6th times x to the, how many more do you need? Remember, exponents add if you have like bases. X to the 7th can be rewritten as x to the 6th times x to the 1st. 6 plus 1 is 7. So this is the same if I say the square root of x to the 7th is the same as the square root of x to the 6th times x to the 1st. Same problem, just written differently. Now what we're going to do is we're going to split that radical sign over our individual factors. So we've got the square root of x to the 6th times the square root of x to the 1st. Now on this first factor, 2 goes into 6 and leaves us with 3. We completely canceled out that root, so our sign goes. And we've got, for this first term, x cubed left without the radical sign. For square root of x to the first, because our power is less than our index, that is simplest radical form. In other words, there are no perfect squares in x to the first, so we'll just leave that as the square root of x to the first. And that is our simplified answer, x cubed times the square root of x. All right, so let's look at some more examples. Let's look at the square root of 8/9. Now again, one of the rules for simplest radical form is you cannot have a fraction underneath a radical sign for your final answer. So we're going to need to split out that square root sign, and I'm going to write the root in the problem. We've got the square root of 8 divided by the square root of 9. Now 9 is a perfect square because 9 is 3 times 3. So if you want to, you can write it like that. 9 is the same as 3 squared. And if your power matches your index, your sign goes. And we can pull out a 3 in your denominator. Or if you have memorized that 9 is a perfect square, you can skip that step and just go directly from the square root of 9 is 3. Okay? Now, square root of 8. 8 is not a perfect square, but it does have a perfect square in it. If you break 8 down, 8 is 4 times 2, and then 4 is a perfect square. It's 2 times 2. So 8 is the same as 2 squared, or 4, and then don't forget that other 2, because it still has to be equal to 8. Okay? So the square root of 8 is the same as the square root of 4 times the square root of 2. And I did 2 steps there. I rewrote 8 as 4 times 2, and then I also split out the radical sign, which is the same, if you want to do this step, as the square root of 2 squared times the square root of 2. Here again, power matches your index, and your sign is gone because your index is gone. Square root of 2 squared, or the square root of 4, is 2. Square root of 2 to the first, nothing more you can do there. You can't break down 2 any further. So you'll just have to leave that as the square root of 2. And then the 3 in the denominator. And if you want to leave off that square root of 2, since it's understood, you can. 2 square roots of 2 divided by 3. All right, let's simplify this problem then. We've got the square root of 9x to the 5th, y to the 7th. Okay, square root. I'm going to put the root out there on the leg, since we're comparing root and index. I'm sorry, root with the power in these problems. Because there's multiplication there, let's split it out. So we've got the square root of 9 times the square root of x to the 5th times the square root of y to the 7th. All right, let's deal with the square root of 9 first. Okay, 9 is a perfect square. The square root of 9 is 3. If you're not sure about that, break 9 down. 9 is 3 times 3. Therefore, 9 can be written as 3 squared. And if you want to do that step, then that would be the square root of 3 squared. Power and index match, and your sign goes. And you can pull out that 3. That step is optional if you recognize that 9 is a perfect square. Now let's look at this factor right here. Square root of x to the 5th. 2 will not divide into 5 evenly. So what we're going to do is we're going to take x to the 5th and write it as x to some power times x to some other power, so that maybe we can simplify it. So, as before, ask yourself, will 2 go into 5? And the answer is no. So decrease that power by 1 and say, if 2 won't go into 5, will 2 go into 4? And the answer is yes. So we're going to rewrite x to the 5th as x to the 4th times however many x's we need to get back up to 5, which would be 1. 4 plus 1 is 5. And we're going to split then that square root sign out to each of those individually. Okay? So now we've got the square root of x to the 4th and the square root of x to the first. Okay, square root of x to the fourth, let's stick with that. 2 goes into 4 and leaves you with 2. That sign is gone because the index completely canceled out. And so now we have 3 times x squared, after we simplified that. Now here we've got the square root of x to the first. Our power is less than their index, so there's nothing more we can do there. We'll just leave that as the square root of x to the first, or the square root of x. Now we're going to do the same thing here with the square root of y to the 7th. 2 will not go into 7, but 2 will go into 6. So we're going to rewrite y to the 7th as y to the 6th times y to the first. 6 plus 1 is 7. Those are all under the square root sign, though, so we're going to put them back under the square root sign. Here there's a common factor. 2 divided by 2 is 1, and it's gone, so our sign is gone. 6 divided by 2 is 3, and so we'll pull that down, and we've got y cubed. And then here, square root of y to the first, there's nothing further you can do with that. Your power is less than your index, so you're left with square root of y here. So now what we're going to do is, simply simplified each factor, we're now going to combine everything back into one radical. Start with the factors that have no radical sign and write those first. We've got 3 times x squared times y cubed. So that gives us 3x squared y cubed. And then recombine your radicals. We've got the square root of x and the square root of y. According to the product rule of radicals, we can rewrite that as the square root of xy. And if you want to put the index back in there, you can. Remember, with square root, though, you don't need to write the index. It's an understood to for square root only. Any other root, you'd have to write it. Okay. Let's look at this problem then. Let's look at the cubed root of 40y to the 10th. All right, cubed root of 40y to the 10th. First step is we're going to split that out into 2 separate radicals. So that would give us the cube root of 40 times the cube root of y to the 10th. 40 is not a perfect cube, so what we're going to do is break it down and see if we can find any cubes in it. So 40, if we bring that up here and do a factoring tree, 40 is the same as 2 times 20. 20 is the same as 2 times 10, and 10 is the same as 2 times 5. So since we're looking for a cube root, we're looking for a factor that appears 3 times, so we can write it as a cube. Notice that this factor of 2 does appear 3 times, and then you have that 5 left over. So 40 is the same as 2 cubed times 5. So that's how we're going to rewrite it. We're going to rewrite 40 as the cube root of 2 cubed times the cube root of 5. Which gives us, let's just stick with that for a minute, which gives us our 3's cancel here and our sign goes, 2 times the cube root of 5 just for the first part of this problem. Now let's look at the cube root of y to the 10th. 3 does not go into 10 evenly, but 3 will go into 9. So we're going to rewrite y to the 10th as y to the 9th times y to the 1st, and then split that cube root out to each of those. Here we can simplify. 3 goes into 9 and leaves us with 3, and the sign goes. And bringing this up here then, we've got the y cubed pulled out because the sign is gone, so y cubed times the cubed root of y to the 1st because our power is less than our index, that's simplest form. And now recombine, write the values without a radical sign first. So 2 times y cubed is 2y cubed. And cubed root of 5 times cubed root of y to the first can be recombined as the cubed root of 5y to the first, or the cubed root of 5y. Make sure that you write the cube, because the root or the index for anything except 2 has got to be written in the final answer. All right, let's look at 3 more examples. Simplify the 5th root of negative 243 z to the 9th. Okay, first step always, split it out. So we've got the 5th root of negative 243 times the 5th root of z to the 9th. Now, negative 243, let's split that out and see what we can figure out in terms of factors. I'm going to go with a positive, and then we'll deal with a negative in a minute. 243 is 3 times 81. And 81 is the same as 9 times 9. And each of those 9s will break down to 3 times 3. So when you completely break down 243, you've got 3 times 3 times 3 times 3 times 3. We're trying to match a power of 5. So notice that the number of times 3 appears is exactly that, which is nice. So we're going to rewrite 243 as 3 to the 5th. Now, negative 243 would be negative 3 to the 5th, because an odd number of negative signs does end up giving you a negative answer. So here, we're going to rewrite negative 243 as the 5th root of negative 3 to the 5th. Okay. And sticking with that for just a minute, our power matches our index, and because our index completely canceled out, our sign goes, and we can pull out that negative 3. Since it's an odd root, we pull out whatever that a value is. Okay, we don't take the absolute value because it's an odd root. So we've got negative 3. Now up here, the 5th root of z to the 9th can be rewritten as the 5th root of, will 5 go into 9? And the answer is no. Will 5 go into 8? No. Will 5 go into 7? No. Will 5 go into 6? No. So we'll have to rewrite z to the 9th as z to the 5th, because 5 will go into 5, times however many more z's we need to get it up to 9. Remember, exponents add. We'll need 4 more. So now we've got the 5th root of z to the 5th times the 5th root of z to the 4th. Our 5's cancel here and our sign goes. And our final answer is negative 3z, because we pulled out this z, times the 5th root of z to the 4th. Okay, so let's look at this example. We've got the 4th root of 32 x to the 12th y to the 5th. All right, first step always is to split that out. So that is the same as the 4th root of 32 times the 4th root of x to the 12th times the 4th root of y to the 5th. Okay, 32. Is 32 a perfect 4th root? And the answer is no. So let's see what it is. If we take 32 and break it down into prime factors, 32 divided by 2 is 16 times 2. And then 16 will break down to 2 times 8. 8 is 2 times 4, and 4 is 2 times 2. So we have 1, 2, 3, 4, 5 factors of 2. However, we're just trying to match the index here. So we are going to group 4 of those 5 together and have 2 to the 4th. And then, of course, we have to multiply it by that last 2 as well, because we still want this to multiply out to give us 32. So the 4th root of 32 is the same as, and I'm going to bring this over here, is the same as the 4th root of 2 to the 4th times the 4th root of 2 to the 1st. Notice here, 4th root of x to the 12th, we can simplify this. 4 goes into 12 and leaves us with 3. And because that completely simplified down, our sign is gone, and we can pull out that x cubed down here. Then 4th root of y to the 5th, because the power is greater than the index, there is more we can do. Will 4 go into 5? And the answer is no, but 4 will go into 4. So we're going to rewrite y to the 5th as the 4th root of y to the 4th times the 4th root of y to the 1st, because 4 plus 1 is 5. Now for each of those, we're going to simplify where we can. Our power and our index match here, and our sign goes. Here, same thing is true. Our power and our index match, and our sign goes. For this factor here, our power is less than our index, so that's simplified already, as is this. So what we're left with here is 2 times the 4th root of 2 times x cubed times y times the 4th root of y to the 1st. And we're going to combine that all together then. Write the factors without radical signs first. So we've got a 2 and an x cubed and a y. So that's 2x cubed y times the 4th root of what's left underneath the root sign, and that would be a 2 times a y, which is the 4th root of 2y for our final answer. All right, one more example. Let's say that we were asked to simplify the 4th root of 162 x to the 7th. All right, 162 x to the 7th. Let's take 162 and break it down and see what it looks like. So I'm going to do that up here. We've got 162. That's an even number, so I know I can take a 2 out at a minimum. So 162 divided by 2 leaves us with 81. 81, of course, is 9 times 9, and each of those 9s will break down to give us a couple of 3s. So 162 is 2 times 3 times 3 times 3 times 3. Now we're interested in matching this index. So we're going to group those 3's together, and we're going to rewrite 162 as the 4th root of 3 to the 4th times the 4th root of that 2 that's left over. Okay? 4th root of x to the 7th. Okay, 4th root of x to the 7th. 4 will not go into 7, but we know that we can't leave it like that because our power is larger than our index. So 4 won't go into 7. 4 will not go into 6 evenly. 4 will not go into 5, but 4 will go into 4. So I'm going to rewrite x to the 7th as the 4th root of x to the 4th times the 4th root of x cubed, because 4 plus 3 is 7. And simplify where appropriate. Our 4's cancel here and our sign goes. Our 4's cancel here and our sign goes. That leaves us with, if we bring it up here, 3 times the 4th root of 2 times x times the 4th root of x cubed, which is the same as 3x times the 4th root of 2x cubed. And that is our final answer. And that brings us to the end of Module 16, Section 10.3 material. You should now complete the homework for Module 16, Section 10.3 found in my math lab. And when you have successfully completed the above homework, proceed to the video for Module 16, Section 10.4.